Okay, hi. This is hopefully the last video for this series on solids, liquids and gases. And I wanted to talk about the pressure law and Boyle's law, which are these two here. One of them has to do with the relationship between the pressure of a gas and its temperature, and the other one has to do with the relationship between the pressure of a gas and its volume. We're going to have to mention briefly again the idea of Brownian motion and the Kelvin temperature, and if any of those two ideas is a bit rusty, please make sure you've watched the last two videos before this one in the series, because they go over those ideas in some detail. Okay, so let me find the section that is related to this. So I've written it out already, a few of the ideas that we need as a prelude to what we're going to talk about. So I don't have to write it down here and bore you, but you should definitely note these down. And the three ideas to discuss here are that so what does it say? The random motion of gas and liquid particles. This I mentioned in the previous video, the one before. The random motion of the gas and liquid particles explains why the pressure acts in all directions at one point. So that's explained by the random motion of the particles. Okay, this doesn't mean gas and liquid particles as in the particles are liquid or the particles are gaseous, right? This just says the particles in a gas or the particles in a liquid. That's different, no? A gas is when the particles are very far apart, and a liquid is when they're closer together, and a solid is when they're even closer and they're just jiggling about a fixed position, right? In a liquid they move around a bit more, and in a gas they move all over the place without keeping any fixed reference to each other while they do that. Okay, so this is an important idea, that it is the random motion of the particles that means the pressure is exerted in all directions at any one point. We've talked about that idea a few times already in the series. The second one is that the speed of molecules increases with temperature, so that as we heat gases in a rigid container, more energetic collisions with the walls occur, and more frequently also, so the pressure exerted by the gas increases, right? So the idea there is that as you give more energy to the gas, its kinetic energy increases, so the speed of the molecules also increases, and therefore they have more energetic collisions and more often, more frequently, and therefore the pressure exerted by the gas goes up if you've got them in a rigid container, right? And this is the pressure exerted by the gas. Even though we often say that the gas is at a high pressure, what we mean by when we say that the gas is at a high pressure is that it is exerting a high pressure in whatever container happens to be holding it at the time. Yes, so hopefully that idea is kind of intuitive to you, that if you heat something you're going to give it more kinetic energy and it's going to bash around more, so the pressure is going to go up. And the last one is that the temperature of a gas in Kelvin, we just mentioned that, is proportional to the average kinetic energy of a gas of molecules. And this is the key here, that they were talking about Kelvin, because to say that it's proportional means that we're saying that when the energy, when the temperature is 0 in Kelvin, right? If this is temperature and this is energy, or kinetic energy, right? We're talking about average kinetic energy. Then when the temperature is 0, it's going to have 0 kinetic energy, and that doesn't happen at 0 degrees Celsius. It does not happen, right? At 0 degrees Celsius you still have lots of energy in the molecules. Even if you have ice and you frozen the water, it's still got a lot of energies moving around, and it's definitely not at 0 energy. It's going to be at 0 kinetic energy, or close to it, very close to it, when you get to 0 Kelvin, and that's why the 0 Kelvin is defined like that. Then as you increase the temperature, the energy is going to go up in a straight line, which is what the word proportional means. You should know that already. And so the Kelvin is a better way of defining temperature for materials, because they actually have a real correspondence with the amount of energy that is present there, instead of just being based like the Celsius is on the boiling points and freezing points of water. Okay, so hopefully that makes good sense, and we can now talk a little bit about the gas laws themselves. So what's happening with the gas laws? Well, there is first one I'm gonna call the pressure law, commonly known as the pressure law, and the other one is Boyle's law, or you can think of it also as the volume law. Not volume law. Okay, so pressure law and Boyle's law. That's an apostrophe there. That's the law belonging to Boyle. Okay, so the pressure law is basically represented by this equation, which is P1 over T1 equals P2 over T2. So you can use this to solve some problems, and we'll do an example of that in a second. In terms of the law, what it says, it basically says what we're just talking about right now, which as you increase the temperature of a substance, you're gonna of a gas, in this case, these laws talk about gases. So yeah, let me put this here in the middle so it's very clear. We're now talking about gases. As you increase the temperature, the pressure increases if you have it in a certain container. So the graph that we could draw here to understand what's going on, also to understand a little bit better what the Kelvin is compared with the Celsius, is this. We can call this degrees C in Celsius, for example, and say that if I had a gas, there are many gases which you can find which at 0 degrees they're still gaseous, and you have to cool them even more to get them to be liquid, and nitrogen and hydrogen are examples of that. So and helium, you can get liquid helium and so on, but you need to cool it a lot more, right? So if this is pressure, here, and this is degrees Celsius, then at 0 degrees Celsius there's still a certain amount of pressure in a gas, and as you heat it more and more and more, which means we go on the x-axis, we go to the right as we raise the temperature. That's not a very good line. Then this happens, the pressure increases with temperature, which is fine. But look what happens at 0 degrees C. There is a finite amount of pressure already present there. And the definition of the Kelvin is basically a continuation of this and saying, well, let's continue this line all the way down, and when it hits, meaning that the gas inside of here I have a container, and here is my gas, and what we're saying is I'm going to take away all of the energy of this gas until it's not moving anymore, and when it's not moving at all, there's going to be zero pressure because it's not hitting the walls at all, and we know that pressure is force over area. So if it's not hitting the walls, there's no force being applied to the containers, and therefore there's zero pressure. So the idea of the 0 Kelvin is this one, where this is minus 273 degrees Celsius. That's the same as 0 Kelvin. So that if we drew the same graph, and instead of having the axis to be Celsius, we had it to be Kelvin, the graph would then start where it's supposed to be at 0 and go up in pressure as the temperature goes up in Kelvin. And the pressure is measured in pascals or newtons per meter squared. So hopefully that makes sense. This is the same graph, but the origin has been shifted because we define the temperature differently. And how do you use this law to answer questions? Let's see. Well, we're gonna do a question using this law, and what we need to remember is super important is that those temperatures in all the gas laws, so like the P and T one, they are all in Kelvin. Okay, so that's what's really important. The formulas work only if you have them in Kelvin. So the question can give it to you cheekily in degrees Celsius, and actually be requiring you to do the conversion. So in this, so I'm going to rewrite it again here. So P1 over T1 is equal to P2 over T2. And let's see what question we can answer with this. Question might say that the initial pressure, the question might say to what temperature would you need to heat a fixed amount of air in a rigid container, which is initially at a temperature of 20 degrees C. So I'm going to call I'm going to call that temperature 1, 20 degrees C, in order to cause the pressure inside of the container to treble. So we want the pressure inside of the container to be 3 times as much. That's quite a tricky question, and I might simplify it a little bit to start with, and then do the more difficult one next. So yeah, what I'm going to do is that let's see what happens to the pressure if we change the temperature and we want to raise, you know, what happens to the pressure if we raise the temperature to twice as much. Okay, so we put the temperature, the second temperature, to be at 40 degrees C, and ask ourselves what's going to happen to the pressure. Now if they give us a gas which is at initially at 20 and then at 40, and they ask us for what happens to the pressure, they also need to give us the initial pressure, P1. They need to give you that, otherwise you can't solve it. Sometimes they tell you that things are at atmospheric pressure, and atmospheric pressure is at 100 kilopascals, so that's 100,000, so times 10 to the 3,000 pascals, right, or 100,000 pascals. That's the atmospheric pressure. So you can always take that to be T1 if they don't give you any, sorry, P1. If they don't give you any, you can take atmospheric pressure to be that, but normally they would give you the pressure of the gas when it starts, so that you can do the change properly. But otherwise, always use this one. Okay, so this question then would say, well, the question is asking me for P2, and P1 over T1 is then 100,000 for P1 divided by T1, which is 20 degrees C. I cannot do this. This is what a lot of people would write and therefore lose marks. I have to do, how did we say that we have to change from degrees Celsius to Kelvin? We have to add 273 degrees, and now we have it in Kelvin. So that would be this that I just worked out, and then we need to put this T2 on the other side of the equation so that we can leave the P2 alone. So we do that by multiplying, because here it is at the bottom it is dividing. So we multiply this by T2, that whole fraction we multiply by T2, and T2 is 40, but again it's 40 plus 273. So we can compute then the pressure at which the gas will be when you've increased the temperature to 40 degrees. And because they're proportional, we should find that the pressure, if the temperature has doubled from here to here, which it has, you should find that the pressure will become twice as much here. And actually I've just done a really important mistake, which is going to be very handy, which will turn out to be useful because it illustrates the importance of the Kelvin compared with the degrees Celsius. It looks like I've doubled the temperature, right? Because I've gone from 20 degrees to 40, so my little brain was making then the leap and saying, well, if I double the temperature, since they're proportional, the pressure should also double. But I didn't notice that the temperature has not doubled. When you go from 20 degrees C to go to 40 degrees C, you haven't doubled the temperature, you've just added 20 degrees to the whole thing. Why is it not a double? Because the temperature Celsius is not the true way of conceiving of temperature. This has not doubled, we've just added 20. Why? Let's write it in Kelvin and you'll see what I mean. What's this in Kelvin? 293. What's 40 degrees in Kelvin? Well, 293 plus another 20, so that's 313. So 313 is not the double of 293. This in temperature in Kelvin, which is the real representation of temperature, the more accurate one, is not twice as much as that, so we haven't doubled the temperature. So there's no reason why the pressure should be double, and you will get that it isn't. You will get a number much closer to the original pressure. So you should get, instead of 100,000, you should get 106, 107 if you round it up, kilopascals. Okay, hopefully that makes sense. That's a really handy thing to realize, because a lot of people would think that it doubles and therefore that's what's going to happen. But for that they would have to give you a gas at 200 Kelvin, which then goes to 400 Kelvin, and then you could say that the pressure would be twice as much, but this is not the case here. So yeah, that should be really handy. So work that out and see if you get around 106, 107 kilopascals, and that should work out to be correct. Now, the more difficult example with the pressure, where they didn't give you the exact numbers, but they were telling you the proportion between one and the next, and all of that we can do in a separate video, because otherwise we won't have time to do Boyle's law here, the one of volumes. So we'll look at more tricky examples of that law later. But for now, this should be enough. So let's have a look at Boyle's law. Boyle's law is the relationship between, instead of, well, the pressure law was between pressure and temperature, and the Boyle's law is between pressure and volume. So what does Boyle's law says? Well, instead of P divided by T, Boyle's law says that P multiplied by V is a constant. So then P2, V2 is a constant. In other words, if they tell you the pressure and volume of a gas at one at one fixed temperature, and then they change one of the variables and the other one changes as a result, and the temperature is being kept constant, then you know that the multiplication of those two numbers before the change equals the multiplication of the two numbers after the change. So that's very handy, because you can use this to make calculations. And for some reason my P came out really weird, so I'm gonna write it down again. And remember, P, I just did it wrong. P is a small letter, so it should look like this: P2 V2. Okay. What does the graph of this look like? Well, if the temperature pressure graph looks like a straight line like that, the pressure volume graph looks different. It looks like an inverse relationship. So the thing, if this is pressure, and in pascals as always, and this is volume in meters cubed as we normally do it, then your relationship should look like that. It should look like that, and like a 1/, relationship. And what does this mean about what's happening in the gas? Well, let's think about it. If I have a syringe like this, or sorry, it's not a very good drawing of a syringe. If I have some kind of gas in here with a lid and a syringe, and I can move the syringe up and down, and my gas is here, whoops, and my gas is here, then as I push on this syringe and I make the volume available for the gas smaller, what's going to happen is that the particles are going to have less volume in which to move, so they're going to collide with the container more often, because they have less to travel before they hit the next wall, right? So how often they collide into the container is going to mean that if I bring down the volume, it's going to bring up the pressure, because it's going to collide more often. Also, pressure is force divided by area, and look what's happening to the area of the surfaces. I'm reducing the area as I bring it down, so actually this is going to be smaller, so therefore the same force in a smaller area is going to produce a bigger pressure, as we've talked about with the stiletto heels. So that's also going to increase the pressure. So for those two reasons, as we decrease the volume, the pressure increases, and that's what's happening here. The volume, you can look at it as being increased on that direction, so as we decrease the volume, the V becomes smaller. Look what's happening to the pressure, it's growing. Okay, and you can also think about it as you increase the volume, there's less collision, so the pressure goes down. So hopefully that makes good intuitive sense. I find that to be the most sort of intuitive one of all. And you can also plot this graph differently. You might see it in a test plotted slightly differently, because instead of plotting pressure against volume, you could say, okay, I want to see if this is really proportional to 1/volume. So what we're saying is that the pressure is proportional to 1 divided by volume. That's why when you multiply by V on the other side, you get that PV is proportional to 1. In other words, that's why this PV is equal to that PV, because it's a constant. It doesn't change. P times V is what's the constant. So what we're saying is that P is proportional to 1/V. So here, if we plot 1 the volume, use the same colors before. If we plot 1 the volume instead of the volume, and here the pressure stays the same in pascals, what's going to happen is that your graph is now like this. It's now a straight line because it's proportional to 1 over the volume. So instead of plotting it against the volume and this thing decreasing, when you plot it against 1 over v, which will be 1 over meters cubed in units, doesn't matter too much, then you'll see that it is a straight line. So therefore, the only way that you're ever going to see a graph that is pressure and volume related with a straight line is when instead of plotting volume here, you plot 1 over v, and then it does work. You will get a straight line. That's very useful in physics to plot it like this, because that tells you that this straight line really means that the relationship is really this one. Pressure is proportional to 1 over volume. That straight line proves it. When you plot pressure and 1 over v and you get a straight line, it means that they're proportional. That's why the straight line is there. But if you plot this curve here, you might say, well, it looks like it's inversely proportional, but we're not exactly sure, and the way to make sure is to make sure that this gives you a straight line when you plot them, p and 1 over v. Okay, so that's Boyle's law, and you can answer questions also like that. They will give you a combination of numbers. They will say, well, there's a certain pressure, there's a certain volume, and then there's a change in it. We change the volume in it, or we change the pressure of it, and then the answer has, the second state has a certain pressure, and now find out the volume. Or they can give you the other way around. They can give you the final pressure and volume of a substance, of a gas, and give you the initial pressure, but ask you for the initial volume before that change happened. And you just know that these two together multiplied need to be equal to those two. So you work one of them and divide it by the other, the third number they give you, and you'll have the fourth one that you're looking for. Make sure that all the units are fine. So your volumes are in meters cubed. These guys are pressures in pascals, which means newtons per meter cubed, and per meter squared, and therefore everything is in meters. And so all of that works fine if you're careful with it. I don't have a lot of time for an example of a question with it, but you find examples in the sheets that I've given you, and you can do examples there. Very similar question to the one we just did. They always give you 3 variables in these cases, and they ask you for the 4th one, and it just is a little bit of algebra in order to find it. Alright. Hopefully that's a set of these videos on revision on the liquids, gases and volumes. Sorry, liquids, gases and solids. And we'll do a few videos more on specific parts of it in equations and things that you might want to ask for, but this revision set is now should be complete. Alright. Take care.